Good morning, everybody. Today is May 6th, 2020. Welcome to Honors Chemistry. Let's go ahead and take a look at the agenda for today, and we'll see what we've got to look forward to. Let's see here. Okay, so yesterday we're starting a new unit this week, kinetics. And honestly, in truth, kinetics is one of my very favorite. It's a really fun topic. It's actually really quick too. Believe it or not, we're going to get through kinetics probably within the next week and a half. So we're going to look at an exam on kinetics by the end of next week at the latest. So it's going to be a really, really quick unit, and we'll fly through it and move on to the next one. But kinetics is fun. It's all about reaction rates and what makes a reaction happen faster. So yesterday, you all watched a couple of videos for me. I hope you don't mind watching a few videos and answering some Google forms. I'm very open to your feedback. So if there's things that you like, things that you don't like, please let me know. This glow stick demo was one I would have had you do in class if we were together, and don't hesitate to try it at home. If you got some glow sticks sitting around, you got younger siblings, this is a fun one to do. Glow sticks are indeed a chemical reaction. What we have inside of a plastic glow stick, if you could open it up, there's a fluid around the outside, and then there's a glass tube on the inside that contains other reactant molecules as well. So when you break the glow stick, the reactants are able to interact with one another. And once they start interacting with one another, then the reaction happens and it releases a just a luminescent glow. I'm thinking about bioluminescence because I don't know if you guys have had a chance to go out to the beach recently at nighttime. I know we're supposed to stay off the beach right now, but if you can get close enough to see the waves when it's really dark, there's bioluminescence out there right now, and it is rad, to say the least. I happen to have some friends that live up on the second story out on the Strand in Hermosa Beach, and so I snuck out there. I kept my social distance. I wore my mask, but I snuck out there the other night as a rebel geek and went to go see that bioluminescence. And the waves as they crash are just glowing. It's really phenomenal to see. So I would highly recommend sneaking out there if you can, but don't go on the Strand and don't go on the beach. You will get a fine. They're fining people, I think, $1,000 for being out on the beach right now. So it's definitely not worth the ticket. But if you know someone and you can sneak out there and maintain your social distance, totally worth it to go check out that bioluminescence. Anyway, glow sticks give off a similar luminescent molecule. And I don't know if you recognize, it was actually Mr. Nadato's voice in this demo, and he put the glow sticks in 3 different temperatures, right? He had an ice bath, a regular room temperature, and hot water. And I hope it was pretty obvious to you that in the hot water, the glow was much brighter. So there's definitely a relationship between temperature and the rate of a reaction. And so we're going to explore that today. If you ever want to slow down the reaction of a glow stick, put it in the freezer and it'll last longer. I don't know if you guys have ever heard that trick before, but it's all kinetics. It's pretty cool. Let's see, what else is there? You watched one of my very favorite videos yesterday. Gosh, I love this one, the TED Ed video on how to speed up chemical reactions and get a date. Love that one because it's all about a high school. So I hope you enjoyed that. And then you watched Mr. Anderson's videos on activation energy, catalysts. Those are some terms we're going to talk about today. And then you got to see the elephant toothpaste demo too. And there's lots of elephant toothpaste demos on YouTube, but I decided to go ahead and post the one that Jimmy Kimmel did just because I find him very entertaining. So we're going to touch on all of these topics today, but I wanted to introduce them to you before we met. So today we're going to start our meeting with Molecule of the Week. I'll answer any questions you might have from the exam last week. You all did pretty well. I sent out the results, and you should be able to see your answer and the correct answer. So if you're having any issues seeing the correct answer or your answer, let me know. And if you have questions, I'm happy to answer those today. But we're moving on from solutions, and we're absolutely going to be applying these concepts of intermolecular forces and solutions throughout the rest of the year. So it is a skill that you're going to be continuously using. So if you don't understand something from that test, please speak up, because otherwise, you know, like I said, everything we learn in chemistry builds on previous knowledge. So if you don't understand solutions, that's going to be a big problem. So please, if you don't understand why you got something wrong on that exam last week, speak up, let me know, let me make sure that we set your brain straight so that you don't make similar errors in the future. Okay, so we'll do molecule of the week. We'll review your exam. There's a simulation I'm going to have you guys work on tomorrow, because we will not be meeting tomorrow. And you saw Mr. Anderson use this simulation in these two videos, at least one of them. I can't remember which one, but we'll take a quick peek at that one. Just I'll have you work on that tomorrow and submit that on Google Classroom by Friday morning. And then I'm going to take you through some guided notes. So if you noticed here in bold, I said, please access or print the Kinetics guided notes prior to our meeting. So we're going to be working on this today. If you haven't gotten a chance to, go over to the classroom. Sorry, it's too much on my screen here. Let's see if I can, no, this isn't right. Go over to the classroom. You'll see that I've uploaded a few things. I've created a new topic in our classwork section. I uploaded this on collision theory. There's really nothing for you to do here. It's just kind of like, it reads more like a textbook than anything else, but it's just a couple pages that has information more in a text style that we're going to be talking about today. This one is what we're actually working on today, this Kinetics guided notes. And I put a copy of my notes here so that you can see the notes filled in. But this is what I want you to have in front of you. I want you to write it out or type it out as we go today. So we're going to be working through this today. So this guided notes intro to kinetics is what I'd like you to have in front of you, either in digital form or printed form. Tonight, I'm going to ask that you just work on this worksheet. This is just extra practice. I should expect that by the end of our lesson today, you should be able to do this. Again, you've got the blank version and the answer key here. If you have any issues, don't hesitate to reach out. And then this simulation. This simulation is what you're going to be doing tomorrow. And it says Google search PHET simulation reactions and rates. I hope this will work on most of your computers. So PHET reaction. And you should get a simulation. It is going to require Java. If you're having issues opening Java on your computer, let me know. But some of the simulations require it, some of them don't. But you have to download this app or this program called Java. It's not going to hurt your computer. Trust me, I've downloaded it on hundreds of computers over my time as a teacher. So if you don't have it on your computer, let me know. Your computer might do something like this to you. I don't know if you guys can see this, where it says it can harm your computer. Do you want to open it anyway? Yes, you do. You might have to go through the security settings a little bit on your computer too. And I can actually show you how to do that now that we're all sitting here together. It says it can't be opened because it's from an unidentified developer. So then I'll show you, if you're on a Mac, here's what you do. I'm going to close this down. I'm going to stop sharing this screen, and instead I'm going to share my desktop. There we go. Okay. So hopefully you can see what I'm seeing now on my desktop. And if you go over here to System Preferences, and then you click on Security and Privacy, And then go over to, oh yeah, general, right here in the general tab. You'll see down here it says allow apps downloaded from, and then you'll see this reactions and rates was blocked from opening because it's not from an identified developer. And then you should be able to click this, open anyway. And then I'm gonna open it, and it's gonna open up this program called Java that I've already downloaded. If you haven't downloaded Java, then go to java.com and download it. It'll just take a couple minutes. But here you have this simulation, and it's kind of fun. It's like a ping pong, reminds me of, not ping pong, a pinball machine, where you have this like launcher that you can pull back on, and you can launch molecules at one another. It's kind of fun. And you can see these are the reactant molecules over here. These are the product molecules. You can raise or lower the temperature, okay? And you can make the molecules move faster or slower as a result. You can change the launching molecule if you want to. You can also pause the simulation if you want to. If you need to at any point, stop. You can do that. You can look at energy diagrams in here. You can look at the separation view, okay? And then once you go over to the mini collisions, you should be able to, actually no, there's to be a way. Oh, you know what? It's because I'm covering this up. Over on the right side over here, you can do something called an angled shot. So you can actually change the angle that you're launching. That one wasn't very good. But you can change the reaction type if you want to. You can design your own. You can reload the launcher and then angle it, maybe launch it. Oh, I did another horrible one. Let's see. I'm gonna get a good angled shot in there. Pull back and then bam. All right, so there's all kinds of things you can do here, but I want you to start. You'll notice that on the simulation that I put up here for you to do, you have a few different objectives here. I want you to be able to describe how an energy diagram can be used to predict whether a reaction will proceed. I want you to be able to describe variables that will affect potential energy of particles and how that relates to the energy diagram. I want you to be able to use the energy diagram to determine activation energy and the sign of delta H, which we'll talk about today, and then draw potential energy diagrams as well. So you'll notice that the simulation isn't too long. It's just, but it's divided into parts. Part one is single collisions, and then I gave you some helpful hints here. So notice the straight versus angled, energy view and separation view. I pointed those out. So read the helpful hints because they should be helpful, hopefully. And then you can do all of these, answer all of these questions. And then part two, many collisions, refers to the next tab over, where you'll click on many collisions, and then you can, you know, use this little pump to pump molecules in, and then you can add other types of molecules. And then you can do mini collisions and watch them react and form products. And this might be a little more helpful to be able to pause the screen at this point, right? So that you can count molecules or answer the questions there. And then part one, part two, and then you've got some energy diagrams. I don't think I'm having you even use the rate experiment. You're not doing any of the rate experiments tab. The only two tabs you're using in the simulation are these two. Okay, so do your best with that. If you have any questions, don't hesitate to shoot me an email, but hopefully it's kind of fun. You know, I like to start off our units with these simulations so that you have a visual for these molecules, so that they're not these, you know, microscopic, invisible molecules, but you can actually visualize what's happening, okay? So that's tomorrow. So you'll be working on the kinetics simulation tomorrow, and that's due, you can upload it with your images, or you can use Cami or DocCam or all those different programs that many of you are using, lots of different ones that are working to submit on Google Classroom. So I think we've got that down pretty well now. All right, so once again, guided notes today, kinetics worksheet tonight, and then tomorrow is the simulation, okay? So if you would please have this at the ready, that would be great. Have that one at the ready. Let me just open them up so I can find them for myself later on this period. I know I'm gonna need it. Hope you all are well in quarantine. I miss you guys. And I love seeing all your Instagram posts. What else? Let's see. I wanted to bring up our test too. And I'm not finding it. Sorry, here it is. Yeah, there's our test too. We're going to talk about that in just a minute. Okay, so let's start today with molecule of the week. Once again, I wanted to choose a molecule of the week that's relevant to our times. We have so much science going on in our world today. And so I chose a molecule that you may have heard about on the news, ritonavir. This is a drug that is an antiviral drug that is in a lot of different trials right now. They're testing its ability to fight off coronavirus. And it's an effective antiviral medication that we've been using against HIV and hepatitis C for many years. But now they're looking at its potential uses for coronavirus. And it seems to be effective when used in combination with other antiviral drugs, although some studies are contradictory. And it was actually kind of fun for me the other night to go through and read some of these scientific studies. Even if you just read the abstract, just Google search ritonavir and coronavirus. I came across some scientific studies, and if you just read the abstract, it's an introduction, kind of summarizes the whole study. There's one that was going on in Thailand where the scientists said it was really effective, but then I found another one in the New England Journal of Medicine that said it has no benefit over typical treatments. So, you know, the scientists are divided on this one. It's a contradictory one. So right now, it's kind of a beautiful thing that the entire world the entire scientific community all over the world is working together toward one common cause today. And that is to get rid of this dang virus that's messing up our lives right now. And so, in some ways it's kind of cool to see everyone working in this collective way. But, you know, I encourage you to look at some of these studies, and if you hear about it on the news, I won't be surprised because they are talking a lot about ritonavir. Anyway, it's a molecule that has carbon, hydrogen, nitrogen, oxygen, sulfur. This is what it looks like. You'll recognize some things here. You'll recognize double, single bonds, some of those wedges and dashes there that show the three-dimensionality of the molecule. Coronavirus is basically, its mechanism of action is and this is how a lot of viruses work, is they come along and they find its host cell and they inject their RNA into the host cell. And basically what they do is they hijack the cell's organelles to produce new viruses. So the RNA gets into our nucleus, and then it forms some messenger RNA that leaves and goes to our ribosomes and endoplasmic reticulum, and it produces proteins, and then these proteins get released from the cell. They use the Golgi apparatus, right? All these organelles that you learned about in biology are basically hijacked by our virus, and they use our organelles to make new little viruses, and then those new little viruses go out and infect other cells, right? And it happens to be affecting the cells that are in our lungs. It's a respiratory virus. And so the mechanism of action of this drug is something, it's called a protease inhibitor. Anything that ends in ASE is an enzyme. So it's an enzyme that cuts proteins once they're made. And so what this drug does is it comes in, and this enzyme comes in and cuts the proteins, but this drug comes in and it blocks the ability for that enzyme to cut the proteins properly so that the new viral proteins can't be formed. And it's pretty cool because if you read some of these abstracts in the scientific studies, they're going to be bringing up words that are now familiar to you. You know enough about science to go and read these scientific studies, which is kind of cool. The efficacy of these drugs is all based on intermolecular attractions, right? Molecular shapes. And this, what we call steric hindrance, means like bulkiness. Like, can they literally fit together like a lock and key? Because if you have an enzyme that looks like this, you have to have a molecule that fits the shape of this active site here, right? And in order to go in there, it has to be able to bind with enough attraction to keep the drug there so that it doesn't fall off, right? So you're going to see words like hydrogen bonding and dispersion forces that are familiar to you now. So it's pretty cool, in this day and age that you young people are now old enough to understand these studies that are coming out from New England Journal of Medicine, and the science behind it. So go out and appreciate the fact that you have that knowledge. All right, so there's your molecule of the week. Like I said, listen up for it. You'll hear it if you listen in the news. All right, next up, I wanted to take a moment and answer any questions you might have about your test from last Wednesday. So I'm going to pull up that screen real quickly, and if anyone has questions about this, you should have been able to see your results. You should have been able to see your results and the correct answer. I tried to set it that way. So were there any questions? If you guys want to speak up, you're welcome to ask questions about it now.
I have a question on numbers 14 and 16, the
Sure.
reasoning for my answer. I got both of those wrong, but I got 13 and 15 right. I couldn't see like the correct answer under. I was just wondering like what the correct reasoning would be.
Okay, so, and can you see your response?
Yeah.
Okay, so the boiling point of salt water is the same as that of pure water. That is false, and the reason why is because when you add salt to water, you're introducing ion dipole interactions. So I was looking for the term ion dipole.
Okay.
You introduce ion dipole interactions, and that you say that those ion dipole interactions are stronger than hydrogen bonds, and they take more energy to break apart, and therefore it takes more energy to boil salt water.
Okay.
Okay, so that was number 14. And number 15 says, what happens to the boiling point of water at high altitudes? This one was a little trickier. I was really looking for the term vapor pressure. Remember when we discussed how vapor pressure is the tendency of a liquid to want to escape and become a gas? And vapor pressure is inversely proportional to the strength of intermolecular forces. In other words, something with weaker intermolecular forces like LDFs has a higher vapor pressure. They're more likely to escape and become a gas because they're not holding on to their liquid molecule friends quite as strongly. And so when you go up to, well, what makes something boil is when the vapor pressure, the tendency to want to become a gas, is equal to the atmospheric pressure. And so I was really looking for you to say something about the definition of boiling point, being when vapor pressure equals atmospheric pressure. And so at high altitudes, that atmospheric pressure is less, which means the vapor pressure can be less and something can boil at a lower temperature. And this was my example of my old colleague, Mr. Torkington, who tried to make a hard-boiled egg while he was camping in the mountains, right? And he couldn't do it. So that's really what I was looking for, was understanding the definition of boiling point relies on vapor pressure and atmospheric pressure. And the atmospheric pressure is less so that vapor pressure can be less. Okay?
Okay, thanks.
Does that answer your question?
Yeah.
Okay, good. All right. Any other questions, concerns, comments, protests about the tests? I will say I do my darndest to write a good chemistry test in Google Forms, but it takes a lot of effort. I'm not going to lie, because Google Forms doesn't allow me to format the way I would like to. Like all these subscripts and superscripts, I have to go to another site and a tiny text generator to get all that. So if you ever see something on these Google Forms that looks a little funny, a lot of the times I'm writing these late at night after my family is all gone to bed so I can finally focus. And if sometimes I make little mistakes, like I make a superscript instead of a subscript or something like that. So I'm doing my best, but it's really a tremendous amount of work for me to write these up in Google Forms. So if you have any questions or something that looks a little funny, please bring it up to me, because I don't have anyone else to proofread this before I send it out your way. I try to catch it all, but I don't always. So, okay, I don't think then, if I'm going to go one more time. Anyone have questions about the exam before I move on to kinetics?
Can you do number 21, please?
21, certainly, yeah. Calculate the mass percent of sodium phosphate if 18 grams is dissolved in a 350 see, there you go, 350 grams of water. Mass percent of sodium phosphate. Okay, so remember, mass percent is a part to whole ratio. So let me write this down, and then I'm going to take it off screen share so you can see this better. So 18 grams of sodium phosphate, and we have 350 grams of water. And I can almost guess what the error was here, because there's a really common error that's made in this type of problem. Remember that a percent is a part to whole ratio, okay? And so it's a mass percent. I believe it asks for mass percent. So that's going to be 18 grams divided by the whole 350 plus 18 grams, right? It's the part, it's Na3PO4 divided by the whole solution. And the solution is solute plus solvent, right? And so if you do this, 18 divided by 350 plus 18 will be 18 divided by 368 times 100. You should get your mass percent. And calculator here. I got let's see, we need 3 sig figs, 4.89%. And hopefully that's the same answer that came up there. Double check here. Oh, I didn't have the answer in there. I'm sorry. I forgot to upload the answer to some of these. It should be 4.89%, I believe. Okay. Did I answer your question?
Yes, thank you.
Okay, excellent. Yeah, a lot of students forget to add the solute as part of their, their whole, right? Because remember, solution is solute plus solvent. Okay. Are there any other questions about the exam before I move on today?
Number 18.
Number 18, certainly. Let's see. Oh no. Say goodbye to it. Let's see. 18. What is the concentration in parts per million of a solution in which 90 grams of aluminum oxide are dissolved in a total solution of 600 mils of water? Water was used as the solvent. Okay, So, let me write this down and then I'll take it off screen share. So we have 90 grams of aluminum oxide. Divided by, in a total 600 mils of water. Okay, so if you look back at your parts per million notes, it's milligrams of solute per kilogram of solvent. The difference is that it's just the solvent in the denominator here. So, okay, so milligrams of solute, if I convert this to milligrams, it should be 0.0900 milligrams of that aluminum oxide. And then kilograms of solvent. Well, if I have 600 mils of water, remember the density of water is 1 gram per mil. And then you can go from grams to kilograms. 1,000 grams in a kilogram gives us, the kilograms of solvent should be 0.600 kilograms. 00, one more, sig fig. Yeah. And so when you divide those two, you should get 0.15 parts per million. And we'll double check that that was the correct answer. No, that's not the correct answer. What happened here? Point milligrams of solute, 0.09 milligrams. Oh my goodness, Mrs. Nielsen, I did something really silly and nobody caught me. When I convert from grams to milligrams, grams are bigger than milligrams. Oh my goodness. Shame on me. This is because I did it in my head. I moved the decimal the wrong direction. We're all human. 90 grams is 90,000 milligrams. Duh. Right? Had I actually gone through the trouble of this, I wouldn't have made that mistake, right? I have to multiply by 1,000, not divide by 1,000. So it should be 90,000 milligrams divided by 0.6. Sorry about that, students. And then that gives us 150,000 parts per million. But you need to represent this to 3 sig figs. And so the only way you can represent this number to 3 sig figs is by doing this scientific notation. 1.50 times 10 to the 5th parts per million. And that's what I was looking for there. Okay, whoops, sorry about that mistake. Any questions? Did that answer your question?
Oh, I guess I was just kind of confused because it says dissolved in a total solution, so I thought you would have to subtract the 90 grams from the 600 milliliters.
That was the wording here. Yeah, I'm giving you the volume of water. There's no way for you to subtract out the solvent there because you don't know the volume that aluminum oxide is taking up.
Okay.
Right? There's no other way to do it properly. So it's just, that was a wording issue. In the future, if that happens, if there's a wording issue, shoot me an email. I'm in front of my computer a lot of the day, and hopefully I can get back to you before you finish the exam so that you can go back and do the problem.
Okay, thank you.
Okay, sorry about that. It sucks because in class, you guys could come up and say, I don't understand this, or raise your hand during a test. But, we're all working with what we've got here. So we're doing our best. Any other questions? about the exam before we move on today? Okay, cool. I was pretty impressed with your scores. I thought you all did very well. So thanks for continuing to have a desire to learn during this distance learning. I know it's not easy. We're almost to summer. We'll make it through. And you guys will be ready for varsity chem next year. I will make sure of it. Okay, let's go ahead and take a look at those kinetics notes. So let's go over here to, where am I? If you would please get these notes in front of you. And I'm just gonna put you guys out into breakout rooms for like 3 minutes. All I want you to do is discuss this background knowledge. You're gonna write the balanced equation for the combustion of methane. We're gonna, you can answer question 2, 3, and then number 4 is gonna test your knowledge of biology a little bit and tickle your brains and dust off some of that biology knowledge. Let me just do this for 2 minutes so you guys can talk to each other without me in the room and work through those 4 problems. And then we'll come back together, we'll go over them, and then I'll deliver some new information to you. So here we go, breakout rooms, starting now, go. Kids, how we doing? Good? Yeah. Are you done coloring? Did you work on I yet? No. You need to keep eating it. Go. Okay? It's good for your belly, honey, and it helps your digestion. You guys need to remember to flex your power and turn off the lights. Mama's still in her session, okay? Nobody's there right now. Okay, so I'm gonna go back in. So bye-bye. I'll be done soon.
What can I do?
Did you work on J yet?
No.
Go work on your J.
Well, let me do it.
Okay, paint by sticker is good too. You guys are doing great. I love you. Hey, Ella and Holden. We're actually in breakout rooms right now. We are working on the something I posted up on Google Classroom last night, and that is this. It says it's called Kinetics Guided Notes, and they're working on the background knowledge. So I'm actually going to call them all back out right now, but if you would please make sure you have this in front of you. We're going to work our way through this for the rest of the period.
Yeah, this happened to me before, but every time I try to join a breakout room, it just kicks me out of Zoom.
That is so weird. What kind of device are you on?
I'm on a MacBook.
I wonder why that's happening. You know what, I'm gonna email Mr. Braskin about that and see. He was here before when it happened. And I'll see if I can help work that out for you. Okay, Holden? Sorry about that.
Thank you.
All right, so everyone's coming back now. Okay. I think we're all back. Okay, so let's take a quick peek at the answers that hopefully you were able to come up with. Balanced equation for the combustion of methane. Don't forget, combustion always requires oxygen and always produces carbon dioxide and water. Well, at least 99% of the time. Don't forget your states of matter, your COSTA. So you always remember your states of matter. You might have water in the liquid or the gaseous phase here. It really depends on the temperature pressure conditions. Remember those phase diagrams we looked at in the last unit where you could predict solid versus liquid versus gas, and it depends on the pressure and temperature on the axis. So actually either one is acceptable here. Liquid or gas is most likely here. Probably not going to be ice if you have a combustion reaction, right? But don't forget that story I told you all about the popcorn when I was a little girl and I pulled the lid off of the popcorn and I let the oxygen in and then the combustion flames could happen, right? So, all right, let's see. So oxygen's always a reactant, carbon dioxide and water are products. Number 2, surface area is going to come up today. So it says, which has more surface area, a sugar cube or powdered sugar? Powdered sugar has more surface area. If you think about like, I don't know, how do I describe surface area? If you could paint the outside, which one would have more paint showing, right? And less hiding on the inside? If I were to paint a sugar cube only on the outside, there'd be lots of little pieces of sugar on the inside that don't have any paint on them. But if I were to paint all the outside of powdered sugar, then everything would be coated with paint, right? There would be nothing hiding on the inside from the paint. So powdered sugar has much more surface area. Let's see, enzymes are catalysts that drive biological reactions. Why are enzymes necessary? Enzymes lower activation energy. And this is something that a lot of biology students come out of biology saying. They lower activation energy to help reactions happen faster. That's probably something you learned in biology. But now I'm going to teach you what that really means to lower activation energy. Okay. And then lastly, what's the building block for each of the following types of organic molecules? Carbohydrates building block is a monosaccharide. So if you ever see monosaccharide, mono means one, saccharide refers to sugars. And if you link lots of monosaccharides together, you get a disaccharide and then a trisaccharide and then a polysaccharide. And that's a carbohydrate. So all those breads and crackers that you're eating, those are monosaccharides that are linked together. Glucose is a monosaccharide. Sucrose is a disaccharide. Okay, so those are building blocks of carbohydrates. Proteins, the building blocks are amino acids. We've talked a little bit about that during molecules of the week. And then lipids units are fatty acids. Okay. And those all require enzymes to build and break down and metabolize the food that you eat every day. Okay, there's lots of chemical reactions going on inside your body. Okay, so let's move on to this part called collision theory. So I'm gonna work through this a little bit together with you all. So the objective for this is that you understand that chemical reactions are not instantaneous. Instantaneous means they happen just like that. Right? A lot of students think that when you mix two reactants together in the same container, voila, all of a sudden there's a chemical reaction, right? But no, there actually has to be collisions between particles. It doesn't just happen because everything's in the same container, right? Molecules have to collide with sufficient energy and the proper orientation in order to react with one another. So I don't know about y'all, but this morning, Ozan was the first to make it into my Zoom session. And he was telling me this story about how he almost overslept and missed our session today. Right, Ozan?
Yeah, of course.
Yeah, thanks, Ozan. So he was sleeping in bed and he wakes up and he realizes, oh my gosh, it's 8:55 in the morning. I'm going to take this off screen share so you guys can see it a little bit better. It's 8:55 in the morning. Oh my gosh, I'm going to miss Mrs. Nielsen's Zoom session, right? So Ozan jumps up out of bed and We'll give him a little happy face. Okay. And what's wrong with this picture? What's wrong with ozone?
I
Anyone
don't
know?
have hair
He doesn't have hair. That's true.
or arms.
He doesn't have arms. Exactly. Right. And it's really hard to put on your pants if you don't have any arms. Actually, we don't know because you were only on Zoom. So, but Ozan did put on some pants this morning. He was telling me, though, his struggles to put on pants. And his pants were over here hanging in his closet. And it's crazy. He's telling me this story, and I'm thinking, wow, this goes perfectly with my lesson on kinetics and collision theory today. So it's really hard to put on your pants if you don't have any arms. So what does Ozan have to do? He has to jump into his pants to get dressed today. So he gets onto his bed. And he decides to use the bounciness of his bed to get into his pants, right? So his first jump, he jumps, but he didn't jump with quite enough gusto to get into his pants. So jump one was, there was not enough energy in his jump, right? So he tries again, goes back, gets back on his bed, starts bouncing a little bit, and he jumps. This time he jumps with more energy to make it all the way to his closet where his pants are hanging, but he ends up upside down and he ends up head first into his pants. That didn't work either, right? Second attempt, Ozan didn't have the proper orientation. Right? So he goes back, tries again, third time's a charm. Let's see, hopefully, because otherwise now he's really going to be right. He actually made it a little early so he could tell me this story. Hopefully, this third time, here we go. There's Ozan. He jumps. Little do you know that Ozan has some ninja skills. He does a flip in the air and he lands. Proper energy, proper orientation, and that's how Ozan got dressed this morning.
That's a true story.
It is. Thanks, Ozan. And I just thought, wow, do you mind? I'm so glad you let me share this with the rest of the students. It's perfect to explain collision theory. So here's the take-home message. Ozan was studying kinetics and he didn't even know it. What we need in order to have a successful collision, right, between Ozan and his pants, he needed sufficient energy and proper orientation, right? So two things that are required in order for reaction to happen is that the molecules must collide with sufficient energy and with the proper orientation. So you have that listed here. I'd like you to write that in the conclusion on yours too. Okay, so when molecules are moving around inside of a reaction container, they're colliding all the time. And you're going to see this in the simulation that you do. They're always bumping into each other. And you need those collisions in order for the reaction to take place, okay? Remember, reactions don't just happen, voila, because they're in the same container. The molecules have to bump into each other. And if they bump into each other, then just because they bump into each other doesn't mean it's a successful collision and they react. They have to collide with enough gusto, with enough energy, and in the proper orientation. They might not collide in the proper orientation, okay? So not every collision is a successful one. As a matter of fact, most collisions are not successful ones, okay? In order for a successful collision that actually causes products or to be produced, you have to collide. There has to be a collision with sufficient energy and proper orientation. Okay, so that's our take-home message from Ozan's story. Perfect. All right, moving on then to measurements that indicate reaction rate. So our objective here is that I want you to know that the rate of a reaction is the decrease in concentration of reactants or the increase in concentration of products with time. Okay, so the way that I like to explain this is I want to describe to you, actually, let's do this. I'm going to take it off screen share again. Here we go. Okay. So my very first job when I was in high school, I oddly enough was working at a deli. I made a lot of beef dip and pastrami dip sandwiches. That's what we were famous for. Although I was a vegetarian, I piled meat really high on these sandwiches. So I like to think of this, or I like to think of my days working at a deli when I talk about reaction rates. So if we envision a sandwich being this reaction, 2 pieces of bread plus 1 piece of cheese yields 1 sandwich. Okay, it's not a meaty deli sandwich, but it's simple way to think of it. So 2 breads plus 1 cheese yields 1 cheese sandwich. Now let's say that my boss, the owner of this deli, was trying to determine the productivity of his business, right? There's a couple of ways he could have done this. He could have looked at how quickly he was selling sandwiches, right? How fast he would sell sandwiches would give him, or how many sandwiches he sold. Or he could also look at how fast he ran out of ingredients, right? And either one would give him an indication of the productivity of his business. So remember, kinetics is all about reaction rates. And this is written at the top of the screen. I think I even forgot to bring it up. So my apologies. But if you go back to the very beginning, you'll see the overall concept of kinetics is that chemical reaction rates depend on factors that influence the frequency of collisions of the reactant molecules. So when it comes to this idea of deli and cheese sandwiches, we could look at, take this little screen share again. I can say that my rate is, this pen is no good. Let's try another one. Can be measured by taking the number of sandwiches produced per unit time, right? Or I could look at the amount of, I'll say, or the amount of ingredients used over time, right? So we can look at the change in sandwiches over the change in time, or the change in ingredients over the change in time, right? And either one of those would tell me the productivity of the deli business, right? This is going to be a positive value. The products are being produced. And this one should be a negative value because the ingredients are being used, right? And so the next question here says, in the following reaction representing the decomposition of water, let's go back to the screen share. The rate of the reaction is best described as the rate at which water disappears, right? So we have water becoming hydrogen and oxygen, the rate at which oxygen disappears, or the rate at which hydrogen disappears. So if you look here, which of the 3 are actually disappearing? Well, the only thing disappearing here is the reactant, right? So we can say that it's got to be A here. So I'll flip right over here. This will be the easier way to do this. Right, the only thing that's disappearing there is the water. So it's got to be A, right? The rate at which water is disappearing. Okay, and so if I were to graph this, you would see a graph that looks something like this, where it says draw a graph that represents the relative amounts of reactants and products over time. Label time on the x-axis and concentration on the y-axis. And so you can see concentration of reactants or products is on the x-axis. Right. The brackets mean concentration of, okay? Whenever you see brackets in chemistry, it means concentration. I may have forgotten to tell you guys that in the last unit. I'm just realizing that. Whenever you see brackets like there, it means concentration, and it's probably most likely in molarity, okay? So you have concentration of reactants or products on the x-axis. You have time on the y-axis. I switched that. Concentration of reactants or products on the y-axis, time on the x-axis, and then we see that products are increasing with time and reactants are decreasing with time. Okay, and so that's what it would look like in a graphical way. So this is what kinetics is all about, is how quickly we can produce or use or produce products or use up our reactants. And really the rate you can notice is changing. This is some calculus here. We won't get into calculus at all, but the rate is really the slope of the tangent line at any point along this curve, right? If you think of it here, let's see if I can do this. You know, at this point, early on in the reaction, I have a lot of reactants around. Okay, when I initially mix all the ingredients in the same beaker, there's a lot of reactants around. So there's a lot of collisions that are happening. And the more collisions you have, the more likely that those collisions are going to be successful ones, right? So the more molecules you have, the more collisions you have, the more likely they're going to be successful. So we have a pretty high rate at the beginning, but over time, the reactants are starting to run out, right? So at maybe this time point here, now I don't have very many reactants in there. And I want you guys to be able to visualize what this looks like. This is where the simulation is going to be helpful. Is as time goes on throughout the course of the reaction, I have very few reactants in the container and more products in the container. And you think about, in order for a reaction to happen, these reactants have to find each other in the container. And if they happen to find each other, they need to collide with sufficient energy and proper orientation. That likelihood becomes much less. And so at that point, at that time point, the slope of the tangent line right there, you can see that if you compare these two slopes, because obviously the rate of the reaction was much faster at the beginning than it was at this time point T here, right? And that's based on the slope of the line. Just because there's fewer reactant molecules, fewer collisions, means that the rate of the formation of products is less, okay? So that's the thing I want you to keep in mind throughout this unit, is that anything that increases the frequency of collisions is going to increase the rate of reaction. I'm going to say that again. Anything that increases the frequency of collisions is going to increase the rate of the reaction. And this makes sense too, because we all live in LA, and it makes perfect sense because we're used to driving on the 405 freeway, which is notoriously crowded with cars. Okay, ironically now it's right now it's not, because nobody's driving to work. But most of the time you hit the 405 freeway and it is packed with cars. And so I like to think of this in terms of car accidents. Where do we think there's more car accidents? Well, LA or, I don't know, Cheyenne, Wyoming. I've never been to Cheyenne, Wyoming, but I don't think that there's that many cars there, right, on the freeways. So if we have collisions between cars, well, the more cars we have, the more collisions there's going to be on the road, right? So that's the idea. Anything that's going to, if you start packing more and more and more cars into smaller space, you're going to get more collisions and therefore more accidents, right? So it's the same concept. If you have more reactant molecules around, then you're going to get more collisions and more products produced at a given amount of time, okay? All right, that is my time for today. And so we're going to have to save part 3 and part 4 for Friday. So you have access to all of my notes here, but I'm going to go through them with you on Friday, so you don't have to worry about it. I'd like to walk you through it just to make sure that I can explain all these parts. In case you get a little caught up with activation energy, there's some notes here, but again, I'll take you through all of this on Friday. So don't worry about understanding all of this yet. We're going to get into part 3 and part 4 then. But when you're going through the kinetics worksheet tonight, you should probably get through at least part of it based on what we've talked about today. If you can't do everything, don't worry about it yet. You'll be able to finish it after I talk to you guys on Friday. But you should be in good shape to do that simulation tomorrow. Okay, and that simulation will be helpful because it's going to help you visualize a lot of the concepts that we'll talk about moving forward. Okay, so I think that's it for today. I'll stick around in case any of you have questions, but otherwise you are free to go. I hope you all are home and well and safe. Take care. Get out there and get some fresh air today. It's a beautiful day.
Thank you.
You're welcome. Bye, guys.
Thanks, Mrs. Nielsen.
Bye. You're welcome. I'm going to stop.
Hey, Miss Nielsen.